Check your thermostat right now. Maybe it says 72 degrees, maybe 75. You press one button and somewhere inside your home, a machine begins pulling heat out of the air. Now imagine the temperature outside is over 100 degrees. The walls have been baking in the sun all day. There is no electrical grid, no compressor, no refrigerant, and no machine capable of producing cold air. Yet people living in some of the hottest regions on Earth built houses that could breathe, towers that moved air without motors, and enormous underground structures that kept winter ice frozen deep into summer. They did not have air conditioning. They turned the entire building into an air conditioner. Because today we have machines that can cool an entire house in minutes. But for thousands of years, humans had nothing. No electricity, no compressors, no refrigerants. So how did ancient civilizations survive some of the hottest places on Earth? The answer is not that ancient people were naturally better at surviving heat. The answer is that they understood exactly how heat moved, and they designed their homes around it. And one of the biggest dangers is something scientists call wet bulb temperature. It is not just about how hot the air feels. It is about whether your body can still cool itself. Your body survives heat because sweat evaporates from your skin. That evaporation removes heat. But when the air is already full of moisture, sweat has nowhere to go. You keep sweating, but your body stops cooling down. That is why humidity can turn ordinary heat into a serious threat. Evaporation slows down, and your body loses one of its most important cooling systems. And yet, communities survived for generations in deserts where summer heat dominated almost every part of daily life. They didn't have air conditioners. So they created something else. They controlled when sunlight entered. They decided where air would flow. They used earth to delay heat, water to absorb it, and nighttime temperatures to carry it away. And the first system did not cool one person. It made an entire building breathe. Level 1. The building that breathed. To understand how far passive cooling could go, we need to travel to the desert city of Yazd, in what is now Iran. From a distance, the city's skyline appears to be covered in strange chimneys. But many of them were not chimneys. They were wind catchers, towers built to control the movement of air. A wind catcher rose above the roofline, where it could interact with air moving across the city. Openings near the top directed that airflow into vertical shafts leading down into the building. Depending on the direction of the wind and the design of the tower, one passage could bring air inward, while another helped warm air escape. But the tower was only one part of the system. Traditional homes in Yazd also used thick earthen walls, shaded passageways, sunken courtyards, and rooms partly below ground. Together, these features created a more comfortable microclimate inside the city. The house was not simply sitting in the desert. Every part of it was controlling heat. The courtyard reduced direct exposure to the sun. The earth surrounding underground rooms slowed temperature changes. The thick walls delayed heat from reaching the interior, and the wind catcher gave moving air a path through the building. It was not air conditioning in the modern sense. It did not manufacture cold air. It managed shade, airflow, thermal mass, and time so effectively that the building itself behaved like a machine. But moving air has a limit. If the day is completely still, a wind catcher has less wind to capture. And even moving air cannot create ice in the middle of summer. So Persian builders attempted something much more difficult. They found a way to keep winter alive long after winter had disappeared. Level 2. The desert buildings that stored ice. The structure was called a yakshal, a word that literally means ice pit. From the outside, some yakshals looked like enormous mud brick domes rising out of the desert, but the most important part was underground. Beneath the dome was a deep storage chamber protected from direct sunlight and insulated by earth and thick construction materials. During cold winter nights, some communities poured shallow layers of water into outdoor basins. The water froze overnight. The next day, another thin layer could be added. This process was repeated until the ice became thick enough to break into blocks and move into the underground chamber. Tall walls could shade the freezing basins from the sun, while the ice storage pit remained protected beneath the ground. Some surviving domed ice houses in Yazd province reach approximately 18 meters in height. These were not tiny household coolers. They were community-scale buildings designed to collect, store, and distribute ice during the summer. Think about what that means. Outside, the summer heat could be intense. Inside, blocks of ice produced or collected during winter remained available months later. No refrigerator, no electrical power, no artificial refrigerant, only night air, water, shade, earth, geometry, insulation, and months of planning. Other cooling systems also took advantage of evaporation through porous clay, damp surfaces, pools, and moving air. But evaporation was never equally effective everywhere. In dry air, water can evaporate more easily and carry heat away. In humid air, that same process becomes much weaker because the atmosphere is already holding more moisture. The Yakchal reveals something even more important. Ancient cooling was not only about reacting to heat after it arrived, it was about planning months ahead, capturing cold when nature provided it, and protecting that cold until it was needed. But storing ice required an enormous structure. Most families still needed another defense, one built directly into the walls of their homes. Level 3. Building a wall against time. But ancient cooling was not only about moving air. Sometimes, the smartest way to stay cool was simply to stop heat from entering your home. For that, we need to look at traditional architecture across hot regions of the Mediterranean, North Africa, and the Middle East. And if you look at traditional buildings there, you will notice two things: bright white walls and extremely thick stone or earthen walls. Those designs were not just about appearance, they were climate technology. The white walls use something called the albedo effect. In simple terms, bright surfaces reflect more sunlight. That means less solar energy gets absorbed by the building. Less absorbed heat means a cooler interior. But the thick walls are even more interesting. Dense walls have thermal mass, which means they can absorb heat without changing temperature immediately. During the hottest hours of the day, the outside of the wall absorbs heat, but that heat takes many hours to travel through the entire wall. By the time it reaches the inside, the sun may already be lower, and outdoor temperatures may have begun to fall. The building has used time itself as a cooling tool. The wall does not destroy heat. It delays it. That delay matters because desert environments often cool significantly after sunset. Once the outside air becomes cooler, the building can release stored heat and prepare for the next day. And this leads to one of the biggest mistakes people make during hot weather. When your home feels too warm, what is your first instinct? Open the windows. You think, I need fresh air. But sometimes, that is exactly the wrong thing to do. If the air outside is hotter than the air inside, opening the window is basically inviting the heat in. Traditional hot climate homes were often operated according to a daily rhythm. During the hottest part of the day, people closed shutters. They blocked sunlight. They kept the hot air outside. Then, when the temperature dropped at night, they opened the home and let cooler air flow through. They were not trying to create cold air. They were protecting the cool air they already had. First, prevent solar heat from entering, then delay the heat that gets through. Finally, release it when the outside temperature falls. It was not one invention. It was a daily cycle. But buildings could only control the environment around the body. At night, people still needed a way to stop their own skin, bedding, and body heat from turning sleep into another battle. Level 4. The Modern Survival Protocol. So how can we use these ancient ideas today? You don't need to rebuild a Persian wind tower. You don't need a stone house in Greece. But the principles behind these systems still apply. First, block the heat before it enters. In the morning, especially before the sun reaches its strongest point, close your curtains and blinds. Pay extra attention to windows facing the afternoon sun. A window is basically a doorway for solar energy. Stop the heat at the door. Second, cool the occupied space, or the person, rather than wasting energy on areas no one is using. Airflow, breathable materials, shade, and personal cooling can make the body more comfortable without cooling every room equally. Third, release the heat at night. Once the outdoor temperature drops below the temperature inside your home, open your windows. Create airflow. Let the hot air escape. Your house needs a daily rhythm. Block heat during the day. Release heat at night. That is the same rhythm traditional builders designed into entire homes and cities. The next time you turn on your air conditioner, remember this. Modern AC is one of the greatest inventions in human history. It saves lives. It transforms cities. And it gives us a level of comfort ancient people could never imagine. But go back to that thermostat for a moment. The number on the screen hides almost everything happening behind it. You do not need to know the direction of the wind. You do not need to calculate when the outside temperature will fall. You do not need to freeze water in winter, carry blocks of ice underground, maintain a mud brick dome, or build walls thick enough to delay the afternoon heat. You press a button. Ancient people had to turn the entire environment into part of the cooling system. We watched the movement of the sun. We studied the direction of the wind. We learned how water, stone, and air could help us survive. The materials have changed. The machines have changed. But the physics has not. The same sunlight, the same wind, the same water, the same planet. The next time cold air flows from a vent and you barely notice it, remember the people who cooled buildings with towers, delayed heat with earth, and carried winter ice into the middle of summer. We did not begin by manufacturing cold. We began by learning how heat moves and building around it. If you enjoyed exploring the hidden technology behind everyday life, subscribe for more stories about forgotten inventions, lost knowledge, and the science hiding in plain sight. Stay cool, and I'll see you in the next one.